Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all in class of elementary number theory. My name is Azmat Ali and today we will discuss properly one of the most important basic topic of elementary number theory, that is the well ordering principle. For elementary number theory, the book that I am using here, this is the one of the well respected book globally, Elementary Number Theory by David M. Burton. So for elementary number theory, throughout our lecture we will particularly focus on David M. Burton book. So let us start from how can we define well ordering principle. Okay, this principle says that every non-empty set of non-negative integers has the least element. This is the simple definition of this principle. This principle says that every non-empty set of non-negative integers has the least element. One of the important things that the David M. Burton will use throughout the text, suppose he says S is a set of positive integer. S is a set of positive integer. The meaning of this statement is, actually, if you are a student of set theory, probably you understand this statement as S is a set of positive integer mean S is actually equal to set of natural number. But this is not true in this text. When he says S is a set of positive integer, he means S is actually a subset of positive integer. Subset of positive integer. And when he say S is set of all positive integer, if he add word all in positive integer, then it means S is now actually equal to set of natural numbers. So this is the basic thing that he will use throughout the text. Further, set of positive integers that is denoted by n, also called set of natural number, have the number 1, 2, 3, 4, 5. Well ordering principle says if you have any subset of n and that set should be non-empty, then that set must have the least element or the smallest element. For example, there are some, I have created some examples here. Let S is set of all integers like 0, 2, 4, 6 up to so on. Then S is a set of non-negative integers with the least element 0. You can see here S is not a completely a set of non-negative integers. Actually here S is a subset of non-negative integers. But the style of this book is that this book will say throughout S is a set of non-negative integer. This book does not use word subset. So the least element of this set is 0. Next, let T is 7, 9, 11, 13 up to so on. The least element of T is 7. In the third example, let U is a set of all non-negative integers. Here n union 0 shows set of all non-negative integers that are 0, 1, 2, 3. So your set U consists on all those non-negative integers that satisfy this inequality, 3n plus 1 less than 20. If you solve this inequality for n, we have 19 by 3, which is approximately equal to 6.33. So your integer should be less than 6.33. So all those integers which are less than 6.33 are 0, 1, 2, 3, 4, 5, 6. So among these integers, the least element of u is 0. Next, how does this principle work? This principle uses the strategy that we claim that a certain set, suppose that set name is S, certain set S has the least element x naught, say, then on the contrary we find an other element y naught such that y naught is smaller than x, that is y naught becomes the least element of S. That leads to the contradiction to our assumption. Purpose of WOP. It can be used for proof of mathematical expression by contradiction. This is the first purpose. It can be used for induction proof. The WOP, well ordering principle. WOP means well ordering principle. The well ordering principle helps prove the division algorithm. WOP is essential in proving the GCD of A and B can be expressed as a linear combination of A and B, that is called the Bayes out lemma. That we will discuss inshallah in our incoming lecture. You will see, to prove Bayes out lemma we will use WOP. Existence of prime factorization. WOP can be used to prove that every integer greater than 1 can be factored uniquely as a prime factorization. Next we discuss the first application of WOP, that is the Archimedean property. What is the statement of Archimedean property? Archimedean property says, if you have two positive integers a and b, then there exists a natural number n such that when we multiply n with a, then na is greater than or equal to b. Suppose your two positive integers, suppose your a is 5 and your b is 100. Clearly a is less than b. Now you can find at least one natural number, one positive integer, such that when you multiply that positive integer with a, your product na will be greater than or equal to b. For example, which n can work here? If you take n is equal to 20 here, when you multiply n with a, this gives us 100. So here na is equal to b. You can find in finite many natural numbers that satisfy this inequality. For example, if you take n is equal to 21, this is the second natural number. If you multiply n is equal to 21 with a, you have 105, which is greater than 100. So the Archimedean property says if you have any two positive integer a and b, you can find a positive natural number, a positive integer n, such that the product of na is always greater than or equal to b. To prove this theorem or property, we use method of contradiction. We say, suppose this inequality does not hold. It means there are some positive integer a and b such that for every natural number n, this inequality does not hold. Assume that the statement of theorem is not true, so that for some a and b, this inequality does not hold. It means na is not greater than or equal to b. This shows na is less than b for all natural number belong to n. Now, I want to use well ordering principle here. As I have discussed above, well ordering principle is valid for the set of positive integers. So, firstly, I construct here a set which consists on entirely all those integers which are positive. So how can we construct them? As here, if you see here, n is less than b. N is less than b implies if we shift na on the left side, this gives us 0 less than b minus na, or can be written as b minus na is greater than 0. This shows that b minus na is greater than 0, that is b minus na, this number is positive for every natural number n. So I construct a set S consist on all those numbers which are of the form b minus na, and clearly these numbers are positive integers. So then the set S consists entirely of positive integers. This implies well-ordering principle holds for S. Now, according to well-ordering principle, set S will possesses a least element, say b minus ma. Suppose that the least element of set S is b minus ma. As n is here natural number, if you know, as you know, if n belong to n, that is n is a positive integer, then the next positive integer, you know, n plus 1 also belong to n. If b minus ma is an element of S, then notice that b minus m plus 1a also lies in S, because if m is positive integer, then m plus 1 is also positive integer, because S contain all integers of this form. Furthermore, we can write this number b minus m plus 1a as, by multiply a inside the bracket, we can write b minus ma minus a. Now you can see here, this complete number is less than this number b minus ma. How? As on the left side, if you observe, we are subtracting a from this number, and on the right side the number is itself here, b minus ma. So clearly b minus ma minus a is less than, this difference is less than this number. If you are unable to understand, suppose this complete number b minus ma, this complete number b minus ma is equal to x, then this becomes x minus a less than x. Now you can see here, x minus a is always less than x. This is true. So this number b minus ma minus a is always less than b minus ma, implies this complete side b minus m plus 1a is less than b minus ma. This shows that b minus m plus 1a is smaller than b minus ma. That is contradiction to our assumption that b minus ma was the least element of S. Hence our original assumption that Archimedean property does not hold is wrong. It means there does not exist any two positive integers for which you can say n is less than b. There are no two such integer exist. Na is always greater than or equal to b for all positive integer a and b. Hence it proves the result. Next we move towards the second application of well-ordering principle, that is actually the first finite principle of induction. In your school in class 11th, I hope you are familiar with the principle of mathematical induction. That can be stated as, when does we use principle of mathematical induction? In order to prove some mathematical statements, mathematical inequalities or formulas, we use mathematical induction, whose statement is, suppose a statement is true for n is equal to, condition 1, suppose a statement is true for n is equal to 1. Condition 2, we suppose statement is true for n is equal to k, then we check whether statement is true for n is equal to k plus 1. If statement is true for n is equal to k plus 1, whenever statement is true for n is equal to k, we say that the statement is true for all all positive integers, or we say statement is true for all natural numbers. This is the statement of mathematical induction. The similar statement for first finite of mathematical induction is, but there is some difference between both statements, but actually basically they are same. Let S be the set of positive integers. Here S be a set of positive integer mean S is a subset of positive integer. S is not a complete set with the following property that satisfies the following two properties. First property, 1 is an element of S. Second property, if k is an element of S, then k plus 1 also belong to S, where k is an integer. If a certain set S, if S satisfies these two properties, then we say that the set S is actually the set of all positive integer. If set S satisfies these two conditions, then we say S is actually equal to set of natural number. In other words, we can say that the set of the natural number satisfied these two properties. To prove the result, we again use a method of contradiction. We suppose on the contrary that S is not actually equal to the complete set of positive integer, that is S is not equal to set of natural number. It means there are some elements in S, there are some gaps between elements of set S. Some positive integers are not elements of set S. So we take another set T. To prove the result, we assume that T be the set of all those positive integers which are not elements of set S. That is, there are some elements belong to set T which are not the elements of set S that can be written mathematically as. And further, we assume that T is non-empty set. At the end, we will show that T is an empty set and S is actually equal to the full set of natural number n. As T consists on positive integers and is a non-empty as by assumption, so well-ordering principle tells us that T possesses a least element. Suppose the least element we denote by A. Because 1 belong to S by hypothesis 1, this is given, 1 belong to S. Because 1 belong to S, certainly A greater than 1. How this inequality hold? How A is greater than 1? As you know, 1 is an element of S and 1 is the smallest positive integer. This is the first positive integer. 1 is actually this first positive integer. When you write for positive integer, the first positive integer is 1, second is 2, third is 3. Now the first positive integer is 1, that is an element of S. It means if 1 belong to S, then 1 cannot belong to T. As A belong to T, it means A cannot belong to S. Then certainly can I say A must be greater than 1, because A is an element of T and T consists on the positive integers, all those positive integers that are not the elements of S. It means A must be greater than 1. A can be 2, 3 or some other numbers. From this A greater than 1, can I write A minus 1 is greater than 0, or can I write 0 less than A minus 1? A minus 1 is clearly less than A. As A is the least element of T and A minus 1 is smaller than A, this shows that A minus 1 cannot belong to T, because although A minus 1 is smaller than A minus 1 is smaller than A, but A is the least element of T by our assumption. It means A minus 1 cannot belong to T. This implies A minus 1 belong to S. By hypothesis B, what is the hypothesis B? The hypothesis B says that if K is some integer that belong to S, then K plus 1 also belong to S. So according to this hypothesis, if A minus 1 is an element of S, then when we add A minus 1, when we add 1 with A minus 1, the next integer will be A. It means this complete number A minus 1 plus 1 by hypothesis B also an element of S. But this element is equal to A, which contradict to the fact that A belongs to T. As A is an arbitrary element of T, that is now an element of S. This shows that there is no element in T and T is empty set. And in consequence, S contain all the positive integers. Or we can say that S is actually equal to set of natural number. In the next lecture, inshallah, we will discuss second principle of finite induction. So take care. See you in the next lecture. Allah Hafiz.